So let's do an example where we use these ideas of time constants to help understand a problem. So here's a problem. This is a current lead, so some kind of conductor, and it's carrying a whole bunch of current during normal operation. And because it's carrying so much current, there's a fairly large generation of thermal energy that happens inside of here, so it has to be cooled, and it's cooled by forced convection on either side using water. So it runs like that for a very long time, comes to some steady state temperature distribution in this kind of on state, and at some time the current lead is shut off, and what that does is actually two things. It shuts off the current, so the ohmic generation drops to zero, but it also shuts off the cooling, so the heat transfer coefficient drops by an order of magnitude. So both those two things happen at time equals zero, and we're interested in looking at the deactivation process. So at time equals zero, we have this steady state temperature distribution inside of here that's associated with ohmic dissipation, and then for time greater than zero, this conductor is going to be cooled down to T infinity in some transient process, right? So let's do the easy part of the problem first. The easy part of the problem being let's figure out what the initial temperature distribution is, right? The initial temperature distribution we get by solving a problem that we could have solved several weeks ago, or I guess several lectures ago. It's a steady state one-dimensional problem. We did problems like this. The differential equation is here. We integrate that twice, and we get this temperature distribution, so this general solution, right? We need to pick C1 and C2 according to the boundary conditions over here. So I have decided to run my computational domain from x equals 0 at the center to x equals L at the edge, right? And I'm making use of this line of symmetry that goes right down the middle of my computational domain. So a line of symmetry is going to be adiabatic, and the reason is because there's no reason for energy to ever want to go from the right side to the left side, given that everything is the same on both sides, right? So lines of symmetry are adiabatic. That's how you model them. And so here my one boundary condition is that at x equals 0, I have no heat transfer, which according to Fourier's law gives me no temperature gradient. And so if I plug this into here, I get this equation. And then at x equals L, I have to balance my conduction into this interface with convection from the interface. And this is convection using the higher forced convection heat transfer coefficient, right? Because this is the steady state temperature distribution that I get before I turn everything off, right? So I plug this guy into here, and I plug this guy into here, and that gives me another equation. So I've got C1 equal to 0, and C2 I solve for using this, and my temperature distribution, let's see if I can find it here, looks like this, right? So I have a high temperature at the center, and then I get this temperature gradient that gets increasingly negative as my conduction rate of heat transfer gets higher and higher, and then this is my temperature drop due to convection. So that's where I start, right? And that we could have done before this lecture. But what I'm interested in now is, what does the process look like of going from this temperature distribution to equilibrium, right? So I know that at equilibrium, eventually my conductor is going to come everywhere to T infinity, right? So I'm going to get this temperature distribution that's 20 degrees Celsius. I'm going to start here. The real question is, going from here to here, what does that process look like, right? And this is a case where you can at least anticipate what the process looks like using these time constants. To get a real solution, an analytical or a numerical solution is going to be kind of involved, and we'll go through how to do that using separation of variables and Laplace transforms and numerical techniques in the next few lectures. But before we do any of that, it's really nice to have some kind of physical feel for what's going to happen. And the way we get that kind of physical feeling in a transient problem is with these time constants. So if you think about what's going to happen when the current lead is turned off, is there's actually two things, right? There's first of all the situation where the temperature distribution inside of the current lead eventually has to come to equilibrium with the surroundings, right? So that's an external equilibration, and we can at least think about that using our lumped capacitance, our external time constant, which is the product of the resistance from the surface to the surroundings times the total heat capacity of the object, right? So in this case, I only have convection, so this is my resistance from the surface to the surroundings. This is the total heat capacity of the object. I multiply those things together and I get 5,600 seconds. So that says it's going to take, what is that, almost an hour for the material inside the current lead to come to equilibrium with its surroundings, right? The other thing that's happening though is kind of interesting, and that is that at time equals 0, I have all this material over here that's really hot, I have all this material over here that's really cold, so there's actually an internal equilibration process that has to occur, right? I'm going to try to, my material is going to try to conduct energy from this hot area over to this cold area, and it does that internally, right? It has nothing to do with what's going on outside. So that is basically a thermal wave, right? That's a conduction thermal wave that has to happen, and it takes a certain amount of time for that energy to move from here over to here. And we know how these things happen now, right? We said that my fundamental equation is this one right here, right? That this is how far a thermal wave moves, and this is the time required for that movement. If I solve this equation for time given a distance, I get this internal time constant right here, right? This alpha, again, is K over rho times C. It's a thermal diffusivity. If I plug in K and rho and C from up here, I find that internal equilibration is going to take about 700 seconds, so about 10 minutes. So this is a case where it's going to take me not very much time to come to equilibrium internally, and it's going to take kind of a long time for this material to come to equilibrium externally, right? So you have a pretty big separation of those two time constants. And based on that information, based on that knowledge, I ought to be able to anticipate what this process is going to look like without ever having to solve the very complicated partial differential equation that underlies this process, right? Initially and relatively quickly, the internal equilibration process is going to happen, and what that's going to really do is take energy from here and plop it over here so that I get some kind of essentially constant temperature, right? That's going to be the outcome of that equilibration. That constant temperature is going to be one that conserves energy. So since it takes so long for external equilibration to happen, during this first 700 seconds, very little energy is going to be lost to the surroundings. So I'm basically going to come to some temperature inside of my object here that has the same energy that my initial temperature distribution had, right? Maybe a little bit less because I am going to lose a little bit of energy, but not very much. And then once that happens, I'm going to get this basically flat temperature that's going to slowly drop down towards T infinity. And that slow drop is going to be basically an exponential, and the time constant of that exponential is about an hour, right? So that's what I would anticipate happening. If I ask you to draw a temperature as a function of position at different values of time, I would expect to see something like this, right? After about 700 seconds, I'm pretty flat. After about an hour, I'm still pretty flat, but now I'm 64% of the way down towards T infinity. After another hour, now I'm 90%, and so you get this sort of exponential drop down to T infinity. That's a lot of insight without a lot of work, right? The other way I could ask you to sketch these results is I could ask you to sketch for me a temperature as a function of time for various values of position, right? So temperature is a function of x, and so x and time. What I'm asking you to do here is draw a temperature as a function of x for various values of time, right? So just different temperature distributions. The other way I could ask you to plot this is, for example, at x equals 0, what does temperature look like as a function of time, right? So at this particular axial location, what does temperature look like as a function of time? Or at other axial locations like x equal L, right? And you can kind of look at this and see what it looks like. Initially, there's this very fast drop down to this sort of average temperature, and then there's a much slower drop down to 20 degrees. If I was over here, initially there's actually a very fast temperature rise up to the average temperature, followed by a very slow temperature drop down to 20 degrees, right? So what that would look like is something like this, right? Temperature is a function of time. Here at x equals 0, I get this 700 seconds or so equilibration. Same thing at x equals L. If I ask you to do it at other positions, right, they'd sort of go like this. And then eventually all positions converge to 1. That's what being flat sort of means. And then I get this drop down to 20 degrees Celsius. One thing that should be kind of sort of obvious from this plot is that after that initial very short internal equilibration process, how does my object want to behave? It sort of wants to behave as if it's a lumped capacitance, right? Basically, when I have this situation where the internal time constant is really fast and the external time constant is really slow, my object wants to come to some uniform temperature and stay there, right? As the surroundings change, it takes the object a long time to adjust to those surroundings because tau external is very long relative to how long it takes to come to equilibrium inside of itself. And that is the crux of the lumped capacitance model. And in fact, we justified the lumped capacitance model using this ratio of 2 conductions. You could just as easily justify the lumped capacitance model using the ratio of 2 time constants. The Beal number can be expressed either way, right? We said that we'd like to look at the ratio of this internal resistance to this external resistance and make sure that this guy is really small relative to this guy, and that's fine. You end up with that equation there. I could have just as easily said, I'd really like to make sure that this internal equilibration process occurs much more quickly than this external equilibration process. And if you went from that sort of perspective at the same thing, you'd end up with exactly the same equation, right? It's also exactly equal to the Beal number, right? So these two ways of thinking about it are consistent with one another. We could ask ourselves the question, what would happen if we calculated these 2 time constants and we found that they were exactly reversed, right? So what if it took a very long time for internal equilibration to happen, right? So here, we could just change the thermal conductivity and the heat transfer coefficient to make this happen. So a very long time for internal equilibration to happen. It takes about an hour for energy to move from this surface to this surface by conduction. But it doesn't take very long at all for external equilibration to happen, right? So in terms of getting energy away from the surface to the surroundings, that's a very quick process, right? What would the temperature distribution look like in that limit, right? So initially I have the same temperature distribution, and if I wait long enough, I'm going to have the same temperature distribution. But going from here to here is going to look very different than it did here, right? So if you think about what's going to happen here, because external equilibration happens so quickly, material very close to the surface is very quickly going to come to equilibrium with the surface, right? But it's going to take a long time for energy to move from these internal locations to the surface, right? In fact, if you think about it, what this is telling you is that the material here at the center of this object doesn't even know anything happened out here at the edge until about an hour after the process starts, right? It takes an hour for the material in here at the center to even start to drop at all, right? Until that point, it's just completely ignorant that anything happened here. If I look at the material here halfway through, it's not an hour anymore. Maybe it's like 15 minutes, but it's the same kind of thing, right? So what you're going to get then is you're going to get a thermal wave that moves very slowly through this object, right? Initially, material very close to the object knows something happens. If I wait a little longer, that thermal wave has moved in a little bit farther, a little bit farther, a little bit farther, and so on, right? So I would get something that kind of looks like this, right? This is temperature as a function of time after about an hour. That's when this thermal wave finally gets to the center, right? And then, it takes longer for everything to sort of move down and get to T infinity. All right, so that's kind of the idea behind these time constants. And again, you're never getting an exact solution with these time constants. All you're ever doing is trying to gain some kind of understanding of what's going on. by using these time constants, and that's really valuable. Again, a lot of times you'll just calculate time constants and you'll find that they are both so small that you don't have to worry about them, or large, or whatever it is, right? And then you can just move on to the next thing in your problem. But there are times where what's going on is very interesting and you need to solve it more exactly, right? These are not exact solutions. And if that's the case, you'd move on to some of the analytical techniques and numerical techniques that we're going to talk about next. But even so, in your back pocket, you want to have these time constants. So when you get answers, you can compare them with your physical understanding of what should be happening in this conduction process.